The stack is the area of a process memory where most buffer overflow occurs. A stack memory overflow can cause a process to crash, information aside of the program to be leaked, and even force the process to start other process. To understand how all this is accomplished, we first need to know a few things about the structure and the behavior of the stack. Process of stack is just a type of a memory buffer which is used to temporarily store data that is being used by the process right now or something later. The stack does this and use the data structure known as queue. So if you have ever stood in a line waiting your turn to do something, you know what it's like a queue data inside of a running process. Sometimes has to do the same thing, that is stand in line with other data waiting to their turn to be used. The term push and pop gives you the impression that data is usually being moved onto and off to the stack as if the stack is a covered belt of an assembly line and widgets are being put onto and taken off on the build. However, pushing and popping is actually just writing and reading data values at a different memory location. And inside the state, push and pop data is only copied to another location, and no data is actually being moved to its original location. The stack is just an array of the adjacent storage location and memory. And the each location is accessed using its own unique memory address like the behavior, and the stack is entirely controlled by a few simple rules of a program used to read and write data to the stack memory location. So we keep track where to read and write the next data item using a variable called the stack pointer, shown here, abbreviated as the SP, the stack pointer, and always hold the memory address of the next element in the stack. That pop operation will data from a copy to push data item to the stack and the program. So first needs to change the stack pointer to hold the memory address of the next address available element on the stack, and then copy the item that being pushed. We now know that the stack is made up of individual elements of a fixed size and a unique location that used to store a data related item, and the data are commonly stored in adjacent locations. So on the stack, a logical grouping of related elements is referred to a stack frame. So a frame is created on the stack and each time a function of the program is called, and the frame is removed from the stack when the function returns. To get a better understanding of how the stack is used during the lifetime of a process, let's just look at a simple C programming. So if you are not a programmer, so there is no need to be panic, and this is just simple code. So here is an example of a C program. It consists of 3 functions, and illustrated that the computer program is fundamentally a sequence of a function calls and the pointer of execution. The main function is called when the operating system starts the program. This is where the execution of the program code begins. The first program statement in main calls is function 1, transferring the point of execution in the code to function 1, and the first program statement and the function 1 then calls the function 2, transferring the point of execution to the code in the function 2, and the only program statement in function to exit the function to and move the point of the execution back to function 1 to the statement of the following to the call to the function. The return statement exits the function 1 and moves the pointer to execution. Back to the main function, the point of execution continues until main itself returns and the program terminates. So what is happening on the stack during all those function call and returns? So I previously said that each time a function in a program is called, a new stack frame is created for that function. A stack frame is like a logical grouping of data pushed onto the stack, which is information used by the program when executing the function stack frames, and also temporarily store the function data when another function is called. So because of that, the function, after calling the function, it used so that the data can be restored, and when the function call returns, this prevents the data from one function from overwriting. And from overwriting the another data from another function, this behavior is extremely important for the proper execution of every program. So let's have a look at how programs are created in what inside of them. Here is a very simple two function program. The main function is called when the program starts and created the main stack frame by pushing the memory of the address of where the main function will return to the memory address of the beginning of the previous stack and the previous stack frame, and creating the storage space for the integer variable x. This is a stack frame to the main function. When the main function calls the function 1, a new stack frame for function 1 is to store the two function parameter variables and the address of the main, where the call of the function 1 will return to the main address of the beginning of the previous stack frame and memory. For the local variable, k is created at the end, as you see in the picture. This is the entire stack frame for the function 1. The next after the frame is where the next frame would be stored if function was called any function. When function 1 returns the main, its frame will be removed from the stack. The stack is managed using several pointers to keep track of the location of the object in the stack. So we already learned that the stack pointer keeps track of the where the next element of the will be pushed or popped of the stack. The free pointer always pointing to the beginning of the stack frame of the current function call, the call pointer. So this pointer makes it easy to find the information associated with the function, and which function is the code to execute it in some CPU architectures. This pointer is referred to as a base pointer in different names, same purpose. And finally, there is an instructor pointer, which point is to just locate and memory and contain the next machine language instruction. This is executed by the CPU itself, and thus instruction pointer steps to the program's code to an incremental fashion, which cause the one instruction to be executed at a time for this reason. So the instruction pointer is also called the instruction pointer or program counter. All of those pointers are actually specialized area of the CPU memory known as like registers, and all dedicated of the specific purpose and are all vital for the operation of the CPU itself.